All right, so we're working on 7.9. We're going to do some examples with improper integrals with infinite limits of integration. So as a class, we're working on number 9, which is definite integral from 5 to infinity. So that's the infinite limit up here of x over the cubed root of 9 minus x squared dx. Okay, so this isn't a friendly integral by any means here. So what we're going to do, class said let u equal 9 minus x squared, so du equals what? Minus 2x dx. Is that true? So we got x dx right there. We can replace that with what? Du over minus 2, right? So if we do that, so this is going to be equivalent to minus 1/2. So I'm going to pull that constant out front. Integral of du. I don't know what the limits of integration are, right? So you could try and replace them in terms of u if you want by plugging that in. I don't really want to. We're going to wait on that. And so we're going to get 1 over what? Cubed root of u, right? Can I take that antiderivative? Yeah. So what? How do I do it? That's minus 1/2. I'm going to rewrite it. So that's u to the 1/3 power, right, on the denominator. So it's u to the minus 1/3 du. From I don't know to I don't know. I'm going to leave the limits off of there, like I said. So what's that? So it's minus 1/2. Add 1, so it's u to the 2/3 divided by 2/3, right? And then I would put plus c, but I don't need that because it's a definite integral. Evaluate from certain limits. So instead of dividing by 2/3, I'm going to multiply by the reciprocal. So I'm going to multiply by 3/2, right? And so that is going to be minus 3/4 u to the 2/3, evaluated from whatever to whatever, right? So just back sub now. So I'm going to come back over here. And when I back sub, put in what it was. U was 9 minus x squared. So this is minus 3/4. 9 minus x squared evaluated from, to the 2/3 power, right? And then evaluated from what? 5 to infinity. Well, we can't do this. So this is a little bit of an issue here, right? So how do I do an infinite limit? Okay, yep. So I'm going to rewrite that. The limit as b goes to infinity. And I'm going to evaluate from 5 to b up here. So my red's not showing very good, but going to go from 5 to b on that. So minus 3/4, the rest stays the same. 9 minus x squared to the 2/3 power. Okay. So if I plug a b in, plug a b in on top. It's minus 3/4. I'm going to keep that out front, and I'm just going to take this limit in here. So it's going to be the limit as b goes to infinity. Let's see, I can plug a b in first. So it's 9 minus b squared to the 2/3 power. And then minus, plugging in 5 here, 9 minus 5 squared to the 2/3 power. 9 minus 25 is minus 16 to the 2/3 power, right? Was that a minus sign that we had over here or a plus? Is this a minus here? Just double checking. Okay, so how can I do that? So we can get the constant, right? So first of all, can I do minus a minus on that or not? And turn it into a plus? No, because this is 2 power, right? Well, what I could do is square the 16. What's 16 squared? 256. So, and then cube root of 256. So I could do that, right? So it'll be minus the cube root of 256, which, what is that? That'd be 2 to the 8th power. Well, 16 is 2 to the 4th, So it's 2 to the 4th times 2 to the 4th, right? Which is 2 to the 8th. So if that was 2 to the 8th power, how many cubed roots could I do? What's 2 to the 8 thirds? 8 divided by 3 is 2 2/3, right? So this is minus 2 2/3. So what am I doing? I'm doing cube root of that. So I can pull a 2 out and I got cube root of 2. So that's the best way to write minus the cube root of 256. So if this was an odd in the back of the book, they're probably going to have this for the last part, not that, right? And that's just the right side. So that's this down here, right? Anyway, now I got the limit as b goes to infinity. So I need to, by the way, this is all going to be times negative 3/4, right? All right. But anyway, so the limit as b goes to infinity. What is this? It'd be negative infinity squared, or excuse me, infinity squared is infinity, right? So anyway, so this would end up being minus infinity to the 2/3 power. So how do I do that? Can I do that? Is this where you got stuck, or where'd you get stuck?
Way back there.
Are you following me so far? Huh? They didn't even go this far. They just show that it diverges. So basically, if a limit exists, it's going to be convergent. I don't know. Well, what would this be? This would be basically minus infinity to the 2/3 power. What's a cube root of minus infinity? I mean, this is fine that we did this. So we'll just go here. This is just some number, right? So it's not going to matter, right? Number compared to infinity doesn't change it when you add or subtract a number from some kind of infinity. But anyway, minus infinity, if you square it, what do you get? Plus infinity. And if you take the cubed root of infinity, what do you get? Well, it doesn't even need to be absolute value, it's just infinity, right? So that explodes to infinity. So since that power, that's going to infinity minus something times a constant. Basically, this is infinity. So what do we know about the integral? It does not approach a specific number, right? So therefore, what we say is the integral diverges. So if it approaches a specific number, let's say we would have got 7 for our answer here, and that's going to be a convergent integral, but it's not. So it approaches infinity because that's a form that doesn't go toward any specific number. Okay. If you take a root, any kind of root of an infinite number, it's still going to be infinite, right? No matter how big the root. If I took the 100th root of infinity, it's still infinity, right? Because infinity means increasing without bound. It didn't change it. Well, I'll make it negative infinity, right? So this is positive infinity times negative 3/4, right? I was just doing the inside part, right? This is going to be minus. We didn't even have to calculate that because this was the issue. But if I multiply times negative 3/4, yeah, this will go to negative infinity. But any kind of infinite limit, you're right. Thank you. So it actually, this integral approaches negative infinity. Okay. So that was number 9. So that wasn't too fun. So let's do, but it is divergent, so it's good to know, right? Okay. Good to know that we can prove that it diverges anyway. All right. So let's try a couple of more. So let's back it up a little bit. Maybe go number 3. Let's do number 3. This is x squared dx, but a to 0 limit as a goes to negative infinity. So basically, we're going to figure this part out first, and then we're going to take that limit, right? So now that it's a little bit nicer, what do you suggest that we do? Let u equal something. How about that? So if I had 5 to the u, then I might be able to figure out, hey, that's some kind of natural log antiderivative from back in chapter 5 or whatever we did like years ago, right? So this is going to be the limit as a goes to negative infinity of, whoops, let's just work on this. I don't need that. Let u equal minus x squared, so du equals minus 2x dx, right? So then we got the x dx right here, and I'm going to replace that, similar deal, with minus 1/2 du. So it's going to be equivalent to the limit as a goes to negative infinity of minus 1/2 integral. The du is there, and I've got 5 to the u du, right? Now, once again, I don't know what my limits of integration are here. I'm not going to worry about that till I'm going to leave them off till I back substitute. Put the originals back on. All right, so what is the antiderivative of 5 to the u power with respect to u? Anybody remember? 5. Is that a front or back flap deal? Times ln u? I think so. I don't know. Where's that at? Back in chapter 5. Is it times ln 5 or divided by ln 5? Right. So the derivative of 5 to the u would be 5 to the u times natural log of 5, right? So the antiderivative of 5 to the u is 5 to the u divided by natural log of 5, isn't it? Okay, so we got the limit of this. And this, of course, is evaluated from I don't know to I don't know. So let's just back substitute and make it right. So now we're going to take the limit as a goes to negative infinity of 5 to the minus x squared over natural log 5, which is just a constant, evaluated from a to 0, right? So we can plug in 0 first. So remember, we do the limit last. A goes to negative infinity. Anyway, plugging in 0, 5 to the 0 power is what? 1. So it's 1 over natural log 5, which is just a constant, right? Natural log 5 is a number, minus 5 to the minus a squared over natural log 5, correct? And then times minus, did I have a minus a half somewhere? I left that off. Minus a half, minus a half, minus a half. Sorry, that was here. Okay. So I needed the minus a half. But now what do? So instead of writing that as 5 to the minus a squared, what can I do? That looks awkward for me. What's your algebra? I'm going to let a go to negative infinity, but instead of doing it here, I don't like negative exponents, so what can you do? Drop it down in the bottom and write it as 5a squared, 5 to the a squared, positive a squared, right? Times natural log 5, and that's a 1 on top, right? So basically, if a goes to negative infinity, what do I got here? So this is minus 1/2 times quantity 1 over natural log 5, and then minus 1 over what? Natural log 5 times 5 to the positive infinity. What's 5 to the positive infinity? Everybody see what I'm doing? I'm just plugging in minus infinity in for a. Yeah. But when you square it, what does it become? Positive infinity. Minus infinity times minus infinity is positive infinity, right? So it's 5 to the positive infinity times natural log of 5, which is just some number. Anyway, what's 5 to the infinity? Power. Infinity, right? And what's 1 divided by infinity? It goes to 0, right? So this part goes to 0. And then, so what am I left with? Minus 1/2 natural log 5, or for a final answer, minus 1/2 natural log 5. Okay? You simplify that. So minus 1/2 natural log 5. Is that a specific number? Yeah, so this is a convergent infinite limit. Everybody good with that? It's convergent. So if it approaches a particular value, we say it's a convergent improper integral with an infinite limit of integration. All okay with that? Long story short, you just got to be good at taking antiderivatives, put it into a form that we've handled before. I haven't assigned anything that we haven't done before, right? So it's trying to memorize and recognize and manipulate those things. Sometimes we got to manipulate it using substitution, which, you know, we can make integrals look easier doing that. Sometimes we got to manipulate using algebraic stuff, right? Sometimes we got to use front and back flaps. Sometimes we got to remember inverse trig antiderivatives, right? So you've done a lot of stuff, haven't you? Get off the film here, clean up a little bit. Any others? You want to do a different one? You want one more out of here?
We did one like 16.
Maybe. I was thinking number 8 or number 19, but number 19 is not like it. With what? Double? Well, let's do 19. 16 looks a lot like what function? I mean, that's one to turn in, right? But what do you think the antiderivative is going to be? Something in, like, what's kind of the base? What's that look like? Arctangent. Right. So just rewrite that as 16 as 4 squared type deal, right? But anyway, let's do, so I can do number 19 here. What's that? This is the definite integral from minus infinity to infinity of sine x dx. Right? So, isn't it or not? Are they asking us to do this 2 different ways? They're asking us to do this 2 different ways or not? Okay, so this is 19A, right, that I'm doing? Okay, so the way we do this, so basically we want to split it up, right, with some constant in between. So sine's continuous everywhere. So once again, we have a couple of things to be able to use this theorem. We need continuity on the open interval, right? Which we have, sine is continuous everywhere. So we're fine to do this, but we're going to rewrite this as definite integral from minus infinity to some specific number. So if you don't have a specific number, what do you think they usually pick? What would be in between negative infinity and infinity? That's an easy number. So they typically pick 0, right? That's just the easiest one. A lot of times when you plug it in. But anyway, I do this. So the derivative, and then of course, how would I rewrite this? This isn't, like, we can't actually do this. So I'd have to rewrite this as the limit as a goes to minus infinity, definite integral from a to 0 of sine x dx, plus the limit as what goes to infinity? B. So we use a for the lower limit, b for the upper limit, definite integral 0 to b of sine x dx. Now, for this to be a convergent infinite integral, improper, this is an improper integral with infinite limits, right? So that's what we're doing in this section. But for this to be convergent, it has to approach a specific number, which would mean that both of these would have to be convergent and approach a specific number, correct? Now we already looked at one of these last time, right? Remember, this is the one that we looked at. We looked at the right side of this, didn't we? And we noticed that the sign goes up and down. This is the area under the curve. So this is always going to bounce between 0 and 1 I think for the area. I don't know what the area was, but anyway, it's always gonna bounce up and down. It can't be negative, according to what Shay said last time, right?
Yeah.
What does it approach a specific number? Well, the derivative of what is sine? Minus cosine. So this is minus cosine x evaluated from 0 to b, and we're going to take the limit as b goes to infinity, right? So once again, I'm not doing both sides. I could have started with this one over here, but if one of them is divergent, then the sum would be divergent, right? Because if it's divergent if it approaches infinity or negative infinity. So if you add anything to positive or negative infinity, you're either gonna get an indeterminate answer or you're gonna get an infinity. So it's gonna be divergent. So just looking at this one, what do we get? Now we got the limit as b goes to infinity of what? Minus cosine b minus what's cosine minus a negative cosine of 0. What's cosine of 0? Cosine's your x, positive 1. So minus a positive 1 is plus a positive 1. I can do that. Really, that doesn't matter. That's just a constant. But the limit as b goes to infinity of minus cosine b. Does that approach a specific number? As b gets bigger, your cosine changes. It does not approach one particular number. It bounces up and down between positive 1 and negative 1, right? Which means that this sum would bounce between 0 and 2, I think. But anyway, this does not exist. So since this side doesn't exist, we could have done the same thing over here and figured out that this side is divergent as well. But this is a divergent improper integral with infinite limits. So it's divergent. So to evaluate ones that both of them go to infinity, split them up, pick a number in between. The easiest number to pick is 0. We're good with that? Okay. I can do one more, or I can move on. So just like everything out to, everything's easy if you know what you're doing. Just gotta get to that point. All right. So, tough crowd today. A little easier. You're like, you guys gotta be the pep. Like you didn't see a prom. Did you stay up late just to feel the pain with everybody else or not? Did you? It's nice. I've seen pictures of everybody except you. Did you go to prom?
Yeah.
Let's post something on our WhatsApp social media. Well, what's going on? Like it's freaking out. Like they're here. Anyway, little poltergeist. You can look that up. Anyway, you gonna do that for us? Sure. I'm not gonna mention your name on film because it's being recorded. Oh no, it's not being recorded. I'm just kidding. I was recording that too. Ready? Okay. What number did you want? One more? You want me to back up the dump truck, do number 8? Oh, let's do number 8. Number 8's fun. Well, not 8. We can't do 8. You gotta do 8.
You can't do it.
Oh, you don't have to do 8. You have to do 8? No, I'll do 8. See if I can do an even one. So what's this one? Definite integral from where to where? Negative infinity to 0? Of what? Okay. X squared e to the x dx. So now what? Could try that, it's not gonna help. So if u equals x squared, then du equals 2x dx didn't really help. U equals e to the x, du is e to the x dx. Doesn't help. What does this look like? And we gotta go to the bathroom? Well, I pee. Sure, yeah. Integration by parts. We're gonna use integration by parts. So first of all, I could rewrite this as the limit as a goes to negative infinity, right? Of integral a to 0 x squared e to the x dx. X squared e to the x. How come when I say then come on? Anyway, I'm just going to work on this part right here. Anyway, we're going to use integration by parts on that, on the box. Okay. So, oh, wait a minute. Don't we let u equal something here? Maybe that's what the unnamed person in the back was saying. I'm going to keep this for future classes, by the way. So, let u equal, we got u dv, right? What do you want to let u equal? First one or the second one? I had it on Tim's theorem over there. Anybody remember? We had one like that. Where is integration by parts? I think we let u equal x squared. And dv equal e to the x dx. And then what do we got to do? We got to come up with du. Du equals 2x dx. And v is the antiderivative of that is e to the x. We don't need the plus c. Remember all that? Okay, this is a good review for the test anyway. So what is, just in general, what is integration by parts? Let me write it over here. Integral of u dv equals uv minus the integral of v du. You remember that? Okay, so what is uv? It's x squared e to the x, so same thing. So it's x squared e to the x minus the integral of v du. So v is e to the x and du is 2x dx. So I'm going to write the 2 out front. Can I do that? And then x in there and then dx there. So I just pulled the 2 out. You okay with that? And once again, do I care what the limit is? No, this is limit from, or the definite integral from a to 0, but I can keep that off for a while if I want. But anyway, we're getting closer, right? But what do you think I got to do again now? I got to do it again. Okay, so I got to use integration by parts again on this one. So this is the breakdown formula that we had with Tim's theorem on sideboard, right? We could have just plugged into my formula, but apparently they erased it. Tina. And, oh, wow, yeah, I threw it right under the bus, didn't I? That goes on criminal record. Touching my stuff. All right, anyway. Oh, I know what she's gonna say. Oh, it's virtual because it's just on the board and it erases. No, it was there. It was real. All right, but anyway, do this again. So what do you want? You want like different letters, or you want to use u bar? U bar equals x, dv bar equals e to the x dx. We got to figure out what du bar is just dx. And v bar, take the antiderivative, is just e to the x plus some constant, which we don't need to worry about. So doing this one, this box is u bar v bar, so x e to the x minus the integral of v e to the x du, which is dx, right? And we can do that one. So this is x e to the x minus, what's the antiderivative of v to the x? E to the x, which we would say plus a constant here, but we don't need it because this is going to be a definite integral from a to 0, right? And then what we got to do is we got to go back and put it all together. Let me do that. And so we had the limit as a goes to a negative infinity of what? The purple box. So it'd be x squared e to the x minus 2 times this, which is the blue box. So the quantity x e to the x minus e to the x. And then this whole thing is going to be evaluated from what to what? A to 0, right? I think did I plug that in right? I think so. We're good here? Everybody good with that? So we just did that breakdown. Once again, you could use Tim's formula there. And then, so let's figure this out. and then take that limit. So once again, if the limit exists to a specific number, it's going to be a convergent improper integral with infinite limit. If it doesn't approach a specific number, so in other words, it explodes to plus or minus infinity or an indeterminate form. Well, indeterminate, we got to be careful, see if there's any other way to do it. But if it explodes to plus or minus infinity, it's going to be a divergent one. All right, so let's plug in 0. What do we get? So it's the limit as a goes to negative infinity. Plugging in 0, what do I get? What do I get here? 0 minus 2 times, in parentheses, 0 minus, what's e to the 0? 1. So it'd be minus 1. So it's minus 2 times minus 1. That's the first part, right? So I actually get something there. I get 2, don't I? I'm going to rewrite it underneath. So it's the limit as a goes to negative infinity of 2, and then minus, plugging a in, what do I get? This looks fun. So it's a squared e to the a minus 2 times the quantity of a e to the a minus e to the a. Did I do that right? Boy, that doesn't look very fun. So let's keep going here. So let me just rewrite it here. So it's a squared e to the a minus 2a e to the a minus and minus is plus 2 e to the a. Everybody agree? Instead of that, hopefully. What could I do here? Factor out of what? Factor out an e to the a times a squared minus 2a plus 2. Yeah. And limit is a goes to minus, this is as a goes to minus infinity. Okay, so what's that? How can I rewrite this? I'm going to rewrite it one more time. Limit is a goes to minus infinity of 2 minus. All right, so here, this is a product. If I'm plugging in minus infinity, I get e to the minus infinity, which is what? That's close to 0, right? Anybody know what e to the x looks like? Like z to the x. It looks like that as it goes to negative infinity, it approaches 0 from the top side. So it's kind of like positive 0 times what? Negative infinity when you square it is positive infinity. Which one dominates here, the a squared or the 2a? A squared. This is the one that's going to dominate. So this is like 0 times infinity, which is what? Indeterminate. So what do I need to do? I need to turn it. This is a great problem. A great problem. Anyway, so I need to use L'Hopital's here. I need to turn it into a quotient. I need to turn the product into a quotient, don't I? How could I do that? So I'm going to rewrite it as a squared minus 2a plus 2, and then over e to the minus a. Can I do that? Make it a quotient. Okay. And now I'm going to take the limit as a goes to negative infinity. But anyway, so what do I get here? Really all I care about, I'm going to go to green, go green. I care about that one. The limit of this one is just 2, right? That's just 2. Correct? So I need to figure out the limit of this one. So the limit as a goes to negative infinity. This would be infinity over, what's e to the minus a minus infinity is e to the infinity, which is infinity, right? So that now it's infinity over infinity, isn't it? So what can I do? I can use L'Hopital's, right? If I use L'Hopital's, I'm going to get 2a minus 2 over minus e to the minus a, right? And what do I get here? I still get infinity over minus infinity, right? Don't I? If you let a go to infinity, I'm just not writing the limit as a goes to minus infinity for sake of time. But everybody agrees this is still infinity over minus infinity, still an indeterminate form. Do we give up and go home? No. Or we do it again. So we're going to use L'Hopital's again on this thing. If I do L'Hopital's again on that thing, what do I get? 2 over e to the minus a, because it's minus a minus e to the minus a, is just e to the minus a. And now if I take, what was I doing? The limit as a goes to negative infinity. What do I get here? That one goes to, that goes to infinity. So 2 over infinity goes to 0 for this part. So this part right here is 0. 2 over e to the a. L'Hopital's 2 over e to the a. Sorry, see if the black works again. L'Hopital's, and we got 2 over e to the minus a. We're going to let a go to negative infinity, so it ends up being 2 over infinity, which is 0. Because e to the minus a goes to infinity. So this is 2 over infinity, which approaches 0. So this part here goes to what? 0, right? So it ends up equaling a final answer of 2, which is a convergent series. You like it? I like it a lot. Yeah. There you go. All right, so 7-9. There you go. Fun examples.